Dear students, after studying this module, you shall be able to know about one group carbon heteroatom disconnection approach. Understand the synthetic approach to carbonyl derivatives. Study the synthesis of ethers and the synthesis of sulfides. Know the compounds made from alcohols. The carbon heteroatom disconnection approach is mainly applicable to the carbon chain attached to any of the heteroatoms like oxygen, nitrogen or sulfur. Here, a bond joins to the heteroatom X to rest of the molecule like a CO, CN or CS group. This point is good point to initiate a disconnection. This is called as one group carbon heteroatom disconnection, as one would need to identify one functional group like ester, ether, amide etc. to make the disconnection. The equivalent reactions are mainly ionic that involve nucleophilic displacement by SN1, SN2 or carbonyl substitutions with amine, alcohols and thiols on carbon electrophiles. The normal polarity of the disconnection of the Rx as shown in the figure will be a cationic carbon synthon 2 and an anionic heteroatom synthon 3 characterized by acyl or alkyl halides as electrophiles and amines, alcohols or thiols as nucleophiles. You can see here that the carbon and the halogen bond, when it gets disconnected or undergoes a retroanalysis, it leads to the formation of the two synthons R plus and X minus. This can be traced back from the reagents, which is R halogen plus and HX, which are the synthetic equivalents to the formation of the given compound. Alternatively, there is also a possibility to use the reverse polarity with the nucleophilic carbon synthon and an electrophilic heteroatom synthon. These type of disconnections are possible only with second or third row elements such as sulfur, silicon, phosphorus and selenium. These synthons are characterized by organometallic compounds like alkyl lithium or alkyl magnesium bromo compounds, which are also called as the Grignard reagents, and also the compounds such as RSCl, trimethyl selenium chloride and diphenyl phosphorus chloride. Here, as we can see in the figure, the disconnection approach gives the anionic synthon where the reagents can be traced back as alkyl lithiums or Grignard reagent. Carbonyl derivatives. The carbonyl derivatives, which are formulated as R C double bond OX, corresponds to carboxylic acid and their derivatives. In these molecules, the point of disconnection is the bond between the heteroatom and the carbonyl group. Therefore, we can make the esters as shown in the figure 11 and the amides as in 13 from the acid chlorides and alcohols or amines respectively as depicted here in figure. An ester undergoes a cleavage from the C double bond O and the oxygen bond, leading to the formation of alcohol and an acid chloride, or amides undergo a cleavage leading to the formation of an amine or an acid chloride. For example, the ester 14 is simply made this way. This ester has been used both as an insect repellent and as a solvent for perfumery. The analysis discloses two accessible compounds, benzyl alcohol and benzoyl chloride. Merging the two with pyridine as solvent and catalyst provides the ester 14. Henceforth, the retrosynthetic analysis has given us an approach to the formation of this ester 14 through benzyl alcohol and benzoyl chloride. Acid chlorides are regularly used in these syntheses as they are most electrophilic in nature of all the other acid derivatives, and as they can be synthesized from the acids themselves with the help of PCl5 or thionyl chloride. The other significant acid derivatives can be made from the acid chlorides or from other compounds above them in the chart of reactivity. So, we can make amides from acid chlorides, anhydrides or esters. The reactivity chart starting from the most reactive to the least reactive has been depicted here in the figure. The hierarchy of the reactivity of the acid derivatives starts from acid chloride, anhydrides, esters and the amides, and the interconversions takes place accordingly. Propanol is another simple example which is used on rice fields as weedicide. Amide disconnection yields the amine 18, which can be made from 2-dichlorobenzene by nitration and further reduction. The sequence of the reactions is very well seen here in the figure. The synthesis is quite simple. There is only point worth noticing is the usage of the catalytic hydrogenation for the reduction instead of use of a messy tin HCl as a reagent. Industry significantly favors catalytic methods with no toxic byproducts. The other disconnection approach for the ester 21 into the alkyl group and the heteroatom is possible by the use of the anion of the acid, for example, in the figure 22, and an alkyl halide R2Br as depicted here in this reaction mechanism of figure. Synthesis of ethers. The disconnection approach for the synthesis of ethers also target the bond between carbon and oxygen. There is a possibility of bond cleavage from either side of the oxygen, as there are two carbon oxygen bonds present in the ethers. For example, the synthesis of ether shown in the structure 24 can possibly be made by two methods, the sequence A or the sequence B, as shown here in the figure. In this case, for the synthesis, the starting materials will be an alcohol 26 or number 27 or an alkyl halide which could be 25 or 28 depending upon what is the sequence being followed, whether A or B. The reaction can take place by following the reaction of the alcohol 26 with the base sodium hydride. The alcohol gets converted to alkoxide anion 29, which further reacts with the benzyl chloride 25 to form the ether 24 in about 85% yield as shown in the figure. We prefer route A as benzyl chloride 25 is more reactive and cannot undergo elimination, while there is a possibility with 28 to undergo elimination and give the alkene as a side product. Let us consider another example. In case of the allyl phenyl ether represented by the structure 32, there are two disconnection approaches which are possible, path A and path B as shown here in the figure. The allyl phenyl ether through the path A can be disconnected to bromobenzene 30 and an allyl alcohol 31. The disconnection through path B is possible with phenol 33 and an allylic bromide 34. The route B is more favorable because nucleophilic substitutions on bromobenzene are comparatively difficult. Hence, the possible synthetic pathway is as given in the figure. Let us look at the synthesis of sulfides. Sulfides are the organic compounds having the chemical structure as R, S and R, where R could be same or it could be a different molecule. The former is called as symmetrical sulfides, whereas the latter would be called as unsymmetrical sulfides. The disconnection approaches for the sulfides are very similar to that of the ethers, as we only replace the heteroatom of oxygen with sulfur. For example, the anion 41 represented by the structure 41, which was derived from the thiol 42, will combine with alkyl halide 40 to make a new carbon sulfur bond and can give R1, S, R2 as shown in the structure 39. The figure represents a complete sequence of reaction. The reaction is simpler with sulfur in comparison to ethers. Thiols are more acidic than alcohols and hence H2S is more acidic than water. Sulfide anion 41 are more nucleophilic towards the saturated carbon than are the alkoxides, and the risk of elimination is quite less in this case. Chlorbenzide, as represented in the structure 43, which is also known by the other names like chlorperacide or chlorsulfacide, is a pesticide and is most commonly used as acaricide, being used to kill mites and ticks. The disconnection of this molecule yields an acidic thiophenol represented by the structure 44 and a reactive alkyl halide 25. The synthesis involves the combining of these two synthons in ethanol with sodium ethoxide being used as a base. Symmetrical sulfides can be synthesized from the alkyl halide and sodium sulfide being used as a base, as shown here in the figure. The product formed in the first step is the monoanion required to prepare the second carbon sulfur bond. The synthesis is merely the combination of the alkyl bromide with sodium sulfide in ethanol. Compounds made from alcohol. Several nucleophile we haven't stated can be used in these reactions. In every case, a nucleophilic heteroatom displaces a leaving group from the compound derived from an alcohol. Alcohol is a good starting material for a compound like ethers, sulfides, thiols, alkyl halides, etc. Here we can see in the figure how the different ethers, sulfides, thiols can be used for the preparation from alcohol. To summarize, the separation of a bond that joins the heteroatom to rest of the molecule like carbon oxygen, carbon nitrogen or carbon sulfur constitutes one group's carbon heteroatom disconnection approach. Acid chlorides are regularly used in the synthesis of the carbonyl derivatives as they are most electrophilic of all the acid derivatives. Esters and amides can be made from the acid, acyl chlorides and alcohols or amines. Ethers can be synthesized from alcohol and alkyl halides. Alkyl halides are made from alcohols by treatment with the reagents such as phosphorus pentabromide or hydrochloric acid and Lewis acid or PCl5 or thionyl chloride. The designing of ether synthesis can be done from two alcohols as a starting material, where one can be converted to the corresponding halide. The disconnection approach for the sulfides are similar to the ethers as we only replace heteroatom oxygen with sulfur. Thiols and the alkyl halide may be good starting material for the sulfide synthesis.